Students, today we're going to be doing partial fraction decomposition and system of inequalities. All right, so let's go ahead and start with partial fraction decomposition. So essentially what we're going to be doing is, well, we have a fraction plus 7 over x squared minus 6. So sometimes in algebra and future in calculus, we want to break it down as simple fractions. Okay? And so for this example, we can actually break it down as 2 over x minus 3 plus -1 over x plus 2. Okay, but how did we do that? Use the partial fraction decomposition, essentially. So our goal is to decompose a complicated fraction into a bunch of small, simple fractions. Okay. So the rules that we're going to be following are as follow. So the first, divide one improper. So when n of x over d of x is an improper fraction, so degree of n is greater than degree of e, divide the denominator into numerator to obtain the following. All right, we're going to have a new n sub 1 x. Then apply steps 2, 3, and 4 to simplify this one. Okay, so factor in the denominator. So completely factor out the denominator into factors, right? So if we take a look at our problem, we were actually be able to factor out, and our factors were exactly x minus 3 and x plus 2, right? This was our factors. If we multiply the denominators, we'll exactly get x squared minus x minus 6. Okay. Then linear factors. So for each factor of the form px plus q to the power of m, the partial fraction decomposition must include the following sum of m fractions. Okay. And then a quadratic factor. So for each factor of the following form, the partial fraction decomposition must include the following sum of n fractions. All right. So it's going to be much easier for us to actually go through the example I showed at the beginning. So let's see. So we know that's also going to be our example 1. So we know we have x plus 7 over x squared minus x minus. Okay. So first step is to factor out the denominator. X squared minus x minus 6 is going to be equal to. So we already know that we can factor it out, and factors are x minus 3 times x plus 2. Okay, so that's exactly what we're going to do. So we're going to have x plus 7, x squared minus x plus 6 is equal to x plus 7 over x minus 3 times 2. So now, most important part is we're going to rewrite it as 2 fractions, right? We simplify the denominator into the simplest fractions possible here. So 2 polynomials. So we're going to have some constant a over x minus 3 plus some constant b of x plus 2, right? So we essentially are reducing the power as we go here. So we have a power 2 here, okay? So that means, and then when we reduce it, we have a power 1, so that means we have power 0 and 0 here. If we were reducing it as a square, we would have a power 1, so we would have ax plus b, for example, right? So, okay. So what is the point of it? So essentially, we know that the denominators are the same. The only difference are going to be we have to find the coefficients of a and b. So that means this numerator must be equal to some of the combinations of a and b in this numerator. So we actually going to combine these fractions right now. So what are we going to have? We know that we're going to have x minus 3 times x plus 2, right? But now, so what does this fraction missing? It's missing a times x plus 2 plus b. So what's b is missing? B has x plus 2, so it doesn't have x minus 3, so we're going to have x minus 3. Okay, so we know that the denominators are the same across all of the fractions here. The only thing that's different is the numerator. So we're going to have our step 2 here. We're going to have, well, we have x plus 7 is actually equal to a x plus 2 plus b x minus 3. So now we got to make sure that we create 2 equations because we have 2 unknowns. So let's simplify the right hand side. So we're going to have x plus 7 is equal to ax plus 2a plus bx minus 3b. Okay, so here we actually have a system of equations. And what we do is, okay, so we have x terms, right? So let's take all of the x terms. Okay, so, and let's factor out. So we're going to have 1 times x plus 7 is equal to, we're going to have a plus b times x plus 2a minus 3b. So we have a variable with a coefficient in front of it plus a constant is equal to a variable, the coefficient in front of it, plus a constant. Okay, so this is our constant here, and this is our constant here. So we actually have a system of two equations. So we have for x terms, we're going to have a plus b must be equal to 1. So when we add a and b, it must add up to 1. And when we have 2a minus 3b, it must add up to 7. All right, perfect. So now we have to go ahead and solve this equation. So let's go ahead and use the techniques that we learned in the linear system. So here's 2 by 2. So what I'm going to do is going to multiply the first equation by -2, add it to the second one, and change the second one. So here I'm going to have negative 5b is equal to 5, and a is equal to 1b. Okay, so we will have that b is equal to -1, and a is going to be 1 minus 1, that's plus 1, which is equal to 2. So that means our original fraction, so x squared minus 6, is equal to, so now we know our a was 2 over x minus 3, plus -1 over plus 2. Okay, and we can, of course, simplify. We can take down that negative. So we're going to have 2 over x minus 3 minus 1 over x. So now we just performed the partial fraction decomposition. Okay, perfect. Now, of course, sometimes we have to work things out in terms of the dividing fractions as synthetic division, and only then applying the partial fraction decomposition. So, and that's going to be our next example. So, a little bit more complicated. So let's take a look at example 2. So if we have something like x to the 4 plus 2x cubed plus 6x squared plus x plus 6. Okay, so what we're doing, we're dividing it by x cubed plus x squared plus x. Okay, perfect. So now our first step here is try to simplify it in some way. So let's actually do a synthetic here. So x cubed plus third. We're just gonna do so x to the 4 plus x 6x squared x plus 6. So we know that x to the 4 over x. So we are just going to be having x, right? Okay, if we have x times x cubed, we're going to have x to the 4. X times 2x squared, that's going to be plus 2x cubed plus x squared. Okay, we're going to be subtracting it. So we're going to end up with 0, 0 at 5x squared plus x plus 6. Okay, so and we're going to keep it as our remainder, right? And why? Well, because we can rewrite our fraction as following. So x to the 4 plus 2x squared plus x plus 6 over x squared plus x. So now it became x plus 5x squared plus 20x 6 divided by x cubed plus 2x squared plus x. Okay, now we have a proper fraction here. So we can actually use partial fraction decomposition. But okay, so our first step is to try to factor out. So x cubed plus 2x squared plus x is equal to, so we can factor out x. We're going to have x squared plus 2x plus 1. Well, perfect. So we have a perfect square here. So we're going to have x plus 1 squared. Okay. So that means we're going to focus specifically on this fraction right here. So we're going to have that 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x is actually going to be equal to 5x over x times x plus 1 squared. So we can start breaking it down here. So we're going to have a over x plus b over 1 plus c over x plus squared. Okay, so now we just simply have three coefficients. And of course, once we have three coefficients, we are able to decompose this fraction. So, okay. So if we simplify, right, so we do the same thing. We multiply them once again. So we're going to have 5x squared plus x 6 over x squared. So that's going to be equal to, we will have it as a x squared plus b x 1 plus cx. Okay, and it's all divided by x squared. So the denominators are the same. So the only thing that we care about is the numerators. So step 2, so we're going to have 5x squared plus x 6 is equal to. So now we have to actually simplify and equate the numbers. So let's see. We have a x squared plus 2xa plus a plus b x squared plus b x plus cx. Okay, perfect. So we're going to have some system of equations, right? So we can notice 5x squared is equal to a plus b. Then 20x is equal to 2xa plus bx plus cx. And the last part is the a, right? A itself is going to be equal to 6. So let's start with that. So we know that a is equal to 6. Then we also have, let's see, so it's going to be 2a plus b plus c is equal to 20. And then a plus b is equal to 5. So we know that a is equal to 6, b 5, so it's going to be 6 plus b is equal to 5, so b is equal to -1. Okay. Then what c is going to be equal to? So we have 12, so 8, so c is going to be equal to 9. Okay, so our actually final equation, right? So x to the 4th plus 2x cubed plus 6x squared plus 20x 6 divided by x cubed plus 2x squared plus x is equal to x plus 6x minus 1 over x plus 1 plus 9 over plus 1 squared. Perfect. So we've done a partial fraction decomposition on this big fraction. Okay. But essentially, right, that's how we're working through. So, and then one more example. Let's go through one more example. So, last example for partial fraction decomposition before we summarize the steps that we have to take once again, and then we're going to move on to system of inequalities. So, okay, now the example 3. So if we have that, the following, so 3x squared plus 4x plus 4 over x cubed plus 4. Okay, so now, again, first step is to factor out the denominator. So we have a proper fraction, so we are okay, right? So we have to factor out. So 3x cubed plus 4, x cubed plus 4x is equal to x times x squared plus 4. Right, this is everything that we can do. We cannot simplify it any further. Okay, so that means we're going to rewrite our fraction. So over x cubed plus 4x. So that's going to be equal to, so we're actually going to have a over x, right? That's because we have that, but this fraction is going to be slightly more complicated because it's x squared, right? We weren't able to simplify it. So numerator must be bx plus c over x squared plus 4, right? Because the denominator is no longer simplified and we do not have first powers, right? We have x squared. So, okay, so that's the difference. This is the important part. So we always have to keep in mind when we're solving such equations. Okay, perfect. And okay, so once again, our step 2, we're going to have 3x squared plus 4x 4, right, is going to be equal to ax squared plus 4 plus bx plus c times, and so we're going to simplify. So 3x for x 4 is equal to, we're going to have ax squared for a plus x squared plus c. And okay, so let's see, we have many equations here. So we're going to have that 3 is equal to a plus b, then 4 is equal to c, and then 4 is equal to a. Right, so let's see. So we have a plus b is 3, c is equal to 4, and 4a is equal to 4. So that means a is equal to 1, b is equal to 2, c is equal to 4. So our fraction actually becomes 1 over x plus 2x plus 4 over x squared plus 4. All right, perfect. And let's think. So we can also have, if we have a repeated fraction, right? So I'll let you do this example for your own. So example 4. So if you have 8x cubed plus 13x over x squared plus 2 squared. Right, so what are we actually doing here? Well, we know that x squared plus 2 is not simplifiable, but we can still factor out as 2 parentheses. So we can actually write it out as ax plus b over x squared plus 2 plus cx plus d over x squared plus 2 squared. All right, so we are actually here. The only thing that gets simplified is, of course, the numerator. Right now, the numerator is going to be in the first powers compared to the third power over here. So you can work it out, and so the answer here, so a should be equal to 8, b should be equal to 0, c should be equal to 3, and d should be equal to 0. You can work out the steps to find a solution. Okay, perfect. So essentially, what we can do is, when we have this equation, so essentially we can solve, and we can, some of the guide. So if we have linear factors, right, as we had in the first example and the second example, substitute the zeros of distinct linear factors in basic equations so that we got, and find, right? I like it to do it as comparing the coefficients. You can plug and check numbers, because sometimes plugging in 0 is much. So for repeated linear factors, we can use the coefficients determined in step 1 to rewrite the basic equation and then substitute other convenient values for x. And then if we have a quadratic equation, of course, we are going to be expanding the basic equation as we did, selecting the terms according to powers of x. That's exactly what I did, right? So we're going from highest power to lowest power, and our lowest power is the coefficients, is a constant specifically, which is power 0. And then we're going to be equating the coefficients of like terms, right, as we did. So based on power. Based on power, we're going to have the like terms. And then we're going to be using system of linear equations to solve for coefficients. And sometimes the systems might be a little bit more complicated, so it's useful to use matrices or any of the substitutions methods or augmented matrices that we learned in the previous lessons. All right, so that would be it for the partial fraction decomposition. And now let's go ahead and move on to inequalities. Okay, so system of inequalities. Very similar to how we were working with system of equations, but essentially, the first thing, let's go ahead and take a look at the graphs. Right, so graphs for system of inequalities is usually it's an application problems. We are going to be interested in some sort of values. So if we want to sketch the graph of inequality in two variables, so we're going to replace the inequality sign by an equal sign and sketch the graph. Right, so we're going to be sketching first equation. So using the dashed line for less than or greater than, and solid curve for less than or equal to or greater or equal to. So that means that the curve that we are sketching is either included or not included. So if it's less than or greater than, it's not included. If it's less than or equal to or greater or equal to, it's included. Okay, so then we're going to be testing point in each of the regions formed by the graph in step 1. So essentially, right, let's take a look at this example of a parabola, right, of a parabolic inequality. So if we have something like this, right? So we have a parabola, and we're saying that y is greater or equal to x squared minus 1. But we're looking at all of the blue points, right? All of the blue points inside, but since we have greater or equal, we are including also the curve itself. So the points on the curve will also satisfy this inequality, right? Everything outside of that curve is going to violate the inequality, so we are not considering it. Okay. Perfect. So that's how we can do it, right? And when we are actually having the system of inequalities, so you can imagine something like this. If we have multiple vertices, right? So we have something like example 2.1. So we're going to have something like x minus y is less than 2, x is greater than negative 2, y is less than 3, right? So essentially, what we are focusing on is, well, first we have to find the intersection points of each part, right? So here, we're finding the intersection parts, right? And intersections are going to be the vertices. So we will have 3 intersection points, right? So intersection points is having one over here, one over here, one over here. Okay? And so it's point A, B, and C. So for us to actually satisfy the equation, right, satisfy these conditions, we have to satisfy each equation, right? So one point must satisfy everything, right? So for example, a point 0, 0 will satisfy all of this. Okay, so that's why this is the solution set. It's within that region, so everything outside of it will violate one or the other equation. Okay, and so what we might have is sometimes we have to be very careful. So drawing, it's always the best way. So first we draw the region, and then we try and visualize it. What are we actually looking for, right? So sometimes don't get it confused that the region might get cut off by another equation, and the region might not look very pretty. Right, so an example of such region would be something like this, right? I have dashed lines, right? So each line is the equation, but here, even though you would think that you would include the triangle, but since we have to satisfy this line right here, and it goes right through the region, and it's talking about like being below, so we only consider this quadrilateral shape here, right? So that's why we'll have to be careful always if you're solving or looking at the equations. Very nice tool to use is Desmos. Desmos shows the regions when you are writing the equations, right? When you're writing the equations, the inequalities specifically, right? It will also use the dashed lines and solid lines and colors to depict what are the regions that you're working on. So a system with no solution, right? Let's take a look at an example 2.2. So no solution is when we have x plus y is greater than 3 and x plus y is less than 1, right? So here, essentially, we're going to have two lines, but we are parallel to each other in the first place, right? We know that they are parallel, and their graph's going to look like this, right? So we know this is the line, x plus y less than 1, and it's not included, and it's everything to the left and then everything to the right. So since the lines are parallel, right, it's the same equation, x plus y, but since they're parallel, they are never intersecting, so their regions are never overlapping. So since they're never overlapping, there's never going to be solution. So this one has no solution. Okay, and sometimes, right, here, previous few examples, we had a bounded solution. So, but now sometimes we might have unbounded solution too. That's completely fine. So example 2.3. So if we have something like x plus y less than 3 and x plus 2y greater than 3, right? Those two equations are different. So that means we will have infinite region, right? Because we have two equations. So here is the infinite region, right? It can stretch out to infinity, but that's fine, right? In application, that's sometimes the case. If we looking for the set of certain points, we might end up with regions like this. Okay, perfect. And that essentially covers the system of linear inequalities. And next lesson, we'll be doing more applicational problems of inequalities and how we can approach them and solve some real-world problems. And in addition to it, we also will do the linear programming for both linear inequalities and linear optimization problems. See you next lesson.